Right, so I'm here today to talk about this concept called serializability. And so in this talk, I'm going to tell you a little bit about what it means, when you want to use it, when you might not want to use it, and I'm going to talk a little bit about my journey through the PhD and how I got interested in this in the first place. So first, a little background on me. I don't even know if I'm a PhD candidate anymore because I defended yesterday, so that was very exciting. Thank you. I don't know what my formal status is right now, but I still have to finish my thesis, so it's not all over. I used to work at Google. I was a software engineer there, where I worked on a storage system, and I also worked a little bit on browser security. And my research at MIT has mostly been about fast transactions for multi-core databases and distributed systems. Okay, so another sort of little bit of insight into what I do and who we are. How many of you guys know this handsome gentleman, James Mickens? Oh, you guys, I'm about to change your world. Okay, so you got to go out there, Google James Mickens, and go read his writings, okay? He is an academic researcher from MSR, Microsoft Research, and he just writes the most entertaining things about computer science that I've ever seen. He also gives really great talks. But I think that this quote is really apt for the kind of work that I do and the kind of work that people in my group do. So I'm going to read it. However, well, just a little background. This is James sort of like theorizing on, in the zombie apocalypse, who he would want on his team, okay? So, however, the most important person in my gang will be a systems programmer. A person who can debug a device driver or a distributed system is a person who can be trusted in a Hobbesian nightmare of breathtaking scope. A systems programmer has seen the terrors of the world and understood the intrinsic horror of existence. Every systems programmer I know who reads this is like, yeah, this is so true. So let's go on this journey together. This is going to be fun. So let's talk about this. I want you to get from this talk an understanding about what the concept of serializability means and why you might want to care about it in your database. So how many people here work on a system that is backed by a database? Okay, great. And how many people have had trouble or have had their lives in some way made worse by this database? Yeah, okay. So databases are complicated, databases are confusing, and we need them to perform really well, unfortunately, for our applications. So here are 3 examples. WhatsApp sees a peak message rate of over 1 million messages per second. This is a little disturbing, but it turns out Facebook is 1/5 of all of the page views in the United States. And Twitter has to handle many millions of messages from mobile devices for analytics. And maybe we aren't all running a WhatsApp or a Facebook or a Twitter, but we can dream. We can hope to get there one day. And data is only increasing in size. Well, that's pretty unfortunate because databases are pretty difficult to scale. So it's pretty easy to scale application servers. You have more traffic to your website, you have more load, more mobile apps, and you just add more servers. It works pretty well. You can handle more traffic. Databases don't work this way. They're stateful. Inherently, it's very difficult to scale your database. And so what people usually do to handle this problem is you buy a bigger database, and then a bigger one, and then a bigger one. And eventually, you're spending a lot of money on some really huge instance with a lot of cores that you're not even using all the time. And someone's like, you need to spend less money on your database, you got to fix this situation, things are slow, things are bad. And so the direction that a lot of people go in is they move towards distributed databases. So smaller databases, we partition our data amongst them, and we can think about things like elasticity and spinning up more databases to handle traffic and things like that. That rarely ever works in practice, but it's a great idea. And so what we're doing is we're partitioning our data amongst the different servers, and this is a distributed database. So here's an example of what that might look like. You might have your widgets table, and you're going to take your widgets table and you're going to choose some partitioning key, and that might be the widget ID or something like that, and you're going to break your table up into ranges and you're going to put them on different servers, okay? So this is called a horizontal partitioning, and what we've got going here is we've got a range of widget IDs on each server. So now, unfortunately, our application servers have to get a lot more complicated. They need to know about the range partitioning, they need to know how to figure out where data is, and they have to probably talk to all the databases in order to put data back together and do different kinds of queries. Now, once we've moved to this model of a distributed database, We've lost a lot of features that we used to have in our one monolithic database. We've lost secondary indexes. We've lost foreign key constraints. We've lost query optimization because oftentimes in this situation, you don't really have queries anymore. You're doing key value lookups. You've also lost joins. And so all of that work has not just disappeared. It's now being done by your web application server. And so there's two problems here. The first problem is that now when we add another web application server, it has to talk to all the databases, and we've got this problem where we're adding a lot of new connections. And also, if you need to add another server, you've got to figure out how to shuffle your data around. And this is really complex. This is a pretty big challenge. It's hard to do this without actually having downtime in your system. And God forbid you actually want to change which key you partition your data on. That could be a nightmare. So this is kind of the setup. This is where I was coming from, this situation where distributed databases were starting to be used more often, but they were kind of terrible and came with this huge set of problems. So I was at Google up until around 2007, and it was a really exciting time because Google was in the middle of building all of these really cool distributed systems. And so I was super excited to be there. I was very into it. Google built MapReduce, which influenced a lot of the big data analytics that we're doing today. They have the Google File System, which was a direct precursor to HDFS. And they had Bigtable, and it just seemed like this was the future. Bigtable is a very large distributed database that's a key value store. So I was very excited about this. These ideas were being developed by other companies simultaneously. There was Cassandra, MongoDB. Amazon published a paper in 2007 about their database Dynamo, which was very influential. And this was a really big thing. This was very exciting. Distributed was the future. So let's talk a little bit about the pros and cons of that. So I went to grad school, and I decided I wanted to work in this area. I wanted to work on distributed systems because I thought they were really cool, and they were the future, and there were really exciting ideas there. And so here's the reason that I think these systems got a lot of traction. First of all, they were in memory, so there was no disk sitting there imposing latency on your query requests. They were highly scalable, very highly scalable. Bigtable, I know for sure, ran on tens of thousands of machines. They were transparently fault tolerant. So when you're running with that many machines, failures are going to happen, and you don't want to have to wake someone up every single time that does happen. And so these systems were great because they replicated for failure tolerance. And they also provided geo-replication. So these days we have users all over the world, and we don't necessarily want to pay that 300 to 400 millisecond latency hit in order to go get our data from halfway around the world. We want to keep data close to users, but we still need to keep that data in sync. And so a lot of these systems provided these kinds of things out of the box. Now here are the cons. These systems had a lot of faults too. There was no schema. So moving from a database to a key value store, you completely lose any idea of a schema to describe your data. They require, and that schema, that organization, that data organization didn't just disappear. Now you kind of had to move it into your key row document design. So if you're setting up MongoDB, you have to decide what goes here, what's an index, what am I doing. With things like Bigtable, keys were very special. You needed to make sure that they were created in such a way that you could do range scans on them. These systems didn't have query languages, and they, at the time, didn't support indexes, though I think some of them do now. They didn't have any notion of transactions, and they really didn't give you very many consistency guarantees. So it was pretty challenging for someone to move from a database to one of these systems. So let's say you've got your single machine MySQL server or Postgres server, and you've got your schema that you very carefully crafted. You've got indexes and foreign key constraints. You've done all this stuff. You've ran queries. You figured out what you can and can't do. And then you're basically just going to throw all of that out the window when you move to a distributed database, which is kind of unfortunate. There's also this cartoon, which I love, by Recursive, and it's pretty old, but it's still very classic. And it's this guy asking, how do I query the database? And the other guy tells him, you have to write a distributed MapReduce function in Erlang. That was the state that we were living in at the time, and we're not too far from the state right now, which is pretty unfortunate. Okay, so Here's another thing we lose, and that I'm going to talk about for the rest of the talk when we jump to a distributed database. We lose this thing called transactions. And some of you might have been using transactions, some of you might not use them, but you didn't even realize you were using them. So in MySQL, I believe autocommit is set to true. And so whenever you run a MySQL query, a single one, you are running a transaction. And so if you're running something like an update query that's going to look at a lot of different rows and potentially change a lot of different rows, that's running with transactional semantics in MySQL. And it's not OK to just drop transactions out of the system. And the reason for that is because it's very difficult to reason about concurrent interleavings of the stuff that we're running in our database. It might result in incorrect and possibly even unrecoverable state. And so let's talk about an example where that happened. So let's say we had a completely decentralized currency which committed transactions, but not the kind I'm talking about, financial transactions, to a log. And there was no way to undo things in the case of fraud. So once you gave your Bitcoins to somebody and it committed to the log, you were pretty much screwed. It was done. So this happened last year. A Bitcoin currency exchange actually lost a lot of money. And here was the quote about it. The hacker discovered that multiple simultaneous withdrawals are processed essentially at the same time, and that the system software doesn't check quickly enough for a negative balance. So this was kind of like spun as a security problem. I don't see this as a security problem at all. This is not a security problem. This is a very classic problem that has to do with transactions. You want to be able to check the balance and do the decrement together at the same time. When you don't do something like that, you can have a whole bunch of people checking the balance at the same time, seeing everything's OK, and then doing a bunch of decrements all at the same time, which makes you go negative. So this exchange didn't lose too much money, but it's a little bit worrisome that there are people out there building software that is addressing something as important as financial data and our money, and it's in a system where it's really seriously not possible to go back and fix it. And they're not really thinking about these concepts. So that's the point of consistency. Consistency guarantees help us reason about our code and avoid subtle bugs. And that's why I think this area is so important and interesting. So consistency is a very misused word in systems, and I think the reason for that is because there were these two different fields. There was the database people and there were the distributed systems people. And they kind of sort of ran in their own circles, and they did different sorts of things. And then, these fields have been moving closer and closer and closer together, and they're pretty much overlapping right now. But it's still people coming from very different backgrounds. And so the word consistency means different things. There's consistency as in ACID. How many of you guys have heard this acronym before? All right, a few of you. OK, good. There's C as in CAP, as in the CAP theorem. There's C as in sequential, causal, eventual, or even strict consistency. There are many different consistency models. And now the thing is, all three of these words, consistency, are talking about different things, which is kind of unfortunate. So let's start with ACID transactions, since that is what this talk is mostly going to be about. So this is what ACID stands for. It stands for atomic, consistent, isolated, and durable. And again, if you are running a MySQL or Postgres database, then you can run ACID transactions. And you can get serializability. And this is what you would type into a terminal in order to do that. So atomic means that the whole thing happens or not. So a transaction is a piece of code, multiple statements, multiple reads and writes. And atomic means you're either going to see the effect of all of those or none of those. Consistent in this context, specifically for ACID transactions, is an application-defined form of correctness. So going back to our Bitcoin example or our bank example, consistent here would mean my idea that balances should never go negative. Isolated is the idea that other transactions, though they might be executing at the same time, don't actually interfere with each other. And durable means that you can recover from a crash. So what this means is that if the database tells you that your transaction has committed, even if it fails, as soon as you get it back up again, you're going to see the database at that point. You're going to see the database at a consistent point, and that's going to include your committed transaction. So most of this talk is going to actually focus on the first three, because I think the first three are what are what have to do with our other definitions of consistency. Okay, so serializability. Serializability is a form of consistency. It's a property of a schedule of transactions. And one thing that I want to stress very heavily is that serializability does not mean serial. It does not mean that you're doing one thing at a time. It means that the effects of what you do are like you did one thing at a time. So here's a slightly more formal definition. The result of executing a set of transactions is the same as if those transactions had executed one at a time in some serial order. That's all that serializability is that the return values from the transactions and what's written to the database and what you give back to the user, it looks like you ran them one at a time, which kind of makes sense. And so in our model, in our ACID model, if we write each transaction to preserve correctness in our database, that means when we start the transaction, things are in a correct state, and at the end, things are in a correct state, then that means that at the end of running these transactions concurrently, our database is also going to be in a correct state. And that means that we get to pretend like concurrency isn't actually happening. We're getting the performance gains of it, hopefully, without actually having to worry about it when we're writing our code. So here's an example of what that really means. Here I have two transactions. The first one is reading two keys, okay, K and J. And just ignore the syntax for a moment. I know it's a little weird, but reads and writes. And this one, transaction 2, is adding 1 to the values for K and J. And so what we want to happen here is that in a serializable execution, we want to see the values of K and J atomically. We want to see both of them at one instance in time. And we want to make sure that we do the adds correctly and also atomically. So let's say we start out with K equals 0 and J equals 0. What are valid values to get back after we've thrown these two transactions at the database? Anybody? Right, K and J equal to 1. Another one is K and J equal to 0. So one thing that could happen is that transaction 1 looks like it ran first, and then transaction 2, and that means you get 0, 0 back. And another one is that transaction 2 ran first, and then transaction 1, you get 1, 1 back. You should never get a 0 and a 1 back. That's what serializability means. Now the benefits of this are that we don't have to reason about interleavings. And we don't have to express invariance anywhere but the code. If we can write our transactions correctly, then the database will promise to execute them for us in a way that looks like one at a time. And I don't know about you, but I do not want to reason about n factorial lines of concurrent interleavings of transactions. That can get very complicated. And it can be very difficult to understand what can go wrong. Unfortunately, serializability atomicity is part of serializability, I would say. Yeah, it looks like the transactions were atomic, that they happened at one instance in time, in order. Okay. So serializability, unfortunately, is kind of expensive. It really does have serious costs to use this as your isolation model. On a multi-core database, this cost comes from serialization and cache line transfers between the different processors. On a distributed database, it's also the serialization or concurrency control and network calls. And so in order to enforce this property in our database, we have to use concurrency control, which usually involves either locking or validation, and essentially some form of coordination. So in order to get around this, people often jump straight to eventual consistency, which is what a lot of key value stores claim to provide. When they don't provide any, I haven't seen a key value store yet that really provides something much stronger than this. So what eventual consistency says is that if no new updates are made to the object, eventually all accesses will return the last updated value. So this concept was at least popularized by Werner Vogels from Amazon. He has a great blog. And I don't know if he actually defined it or not, but it was definitely one of the first times that I've seen it, and this was how he defined it. Now, I'm going to make a little bit of an edit here, because I'm sure you guys have all heard that in a distributed system, there's not really a very good, consistent notion of time. So what does the last updated value mean? Your last, my last, some other server's last, the client's last? Who knows, right? So we don't really know what last means in this context. And so it's not really the case that it's getting updated to the last value. Eventual consistency just says we're going to get the same value. And also that key part up there, if no new updates are made to the object. So when does that actually happen in a system? I'm wondering who runs these systems where you actually stop writing for some period of time, and you can give some undetermined period of time, by the way. This period of time isn't bounded. And you can let your servers kind of coalesce into the same state. This doesn't actually happen when you're running a product. And this says nothing about multi-key transactions. So despite the fact that you're getting, things are converging to the same value, you're not going to be able to do the bank balance thing that I talked about. This property definitely does not give you that. So a slightly stronger form of consistency, well, a much stronger form of consistency is sequential consistency. And the best way I've found to think about this is it's what your laptop is doing right now. So you've got multiple processors, and each of those processors has a cache. And what's happening is that your processors, the hardware, is keeping your cache sequentially consistent. And I'm using that term a bit loosely because technically it's not even sequential consistency, but unless you're building locking protocols or things like that, we're not going to worry about it. It's close enough to sequential consistency. And so what's happening here is that your processor is tracking what cache lines it's reading and writing, and it's making sure that those stay in sync across all of the caches. So what sequential consistency means is that when you're doing a series of reads and writes, they happen in some order. The reads and writes correspond to happening in an order. And usually they give you the feature as well that if you're on a processor, they look like they're happening in the order the processor executed them in. So let's start with this example right here. So here are 3 processors, and they're doing a series of reads and writes to the same variable. So the first one's writing A, then the second one is writing B to X, and then the third one is reading A and then reading B. Does this look legal to you guys? Does this look correct?
Yes.
Yeah, okay, well, yeah, maybe it was obvious. But, and the reason for that is because we're allowed to reorder reads and writes between the different processors. And so this is a correct interleaving of this, where we can just kind of shove that write on processor 2 down and pretend like it happened after the read. Now how about this one? We're writing A, then we're writing B, then we're reading B, and we're reading A. Nope, this is correct. So the reason that this is correct is we can shove that write even further down, and we can create something that looks like this. So sequential consistency, even though it's one of the strongest forms of consistency, is still really confusing. I still get really confused by what's allowable and what's not under this model. So there's an even stronger form of consistency out there called external consistency. And I think this is occasionally referred to as linearizability. And the idea here is that it's what sequential consistency promises you. You're going to see the reads and writes in some order that makes sense, but the results are actually going to match time. So to me, this is the only thing that actually makes sense in the world. This is the only way that I can actually reason about what's going on. And one way to think about it is as though there's a little detective, a little external observer sitting there looking at reads and writes and watching what's happening. So if we're looking at our previous example, where we had the write to A and the write to B, if those really happened at different points in time, then an observer could have come in and seen that the write to B happened after the write to A. And so then if processor 3 read them in this order, the observer would know that this was incorrect. It would know that since there weren't any other writes to X, that this was an incorrect interleaving. So this is the strongest form of consistency. Everything's matching this sort of one copy. Things happen one at a time, according to when someone actually issues a read or a write. So this is the type of consistency that is being talked about when you hear the words the CAP theorem. So this stands for consistency, availability, and partition tolerance. It was first proposed by Eric Brewer from Berkeley in 2000 at a talk in PODC, which is a distributed systems conference. And it turned out that it's a rephrasing of a much older result, the FLP result. And so this was done in 1985 by Nancy Lynch at MIT and some other people. And okay, so what Eric Brewer was saying is that I mean, ostensibly what he said and what's quoted is, out of these 3, you get to choose 2. But what he was really saying is that partition tolerance is a failure model. Sometimes your servers won't be able to talk to each other, and sometimes you're not going to be able to know how long they're not going to be able to talk to each other. And because you don't know a bound on this length of time, then you have to decide whether or not you're going to process reads and writes potentially incorrectly, violating consistency, or not. And so that's the choice that I think that he's really talking about. Now, one thing that's important to note, the FLP result is actually very cool if you want to go read this paper. There's this very cool construction in it where they prove that it's impossible to reach consensus with a group of servers even if there's one faulty process. And the reason for this is because this faulty process can just always do the wrong thing at the right time. So no matter how close you get to deciding amongst all of your servers, this one faulty process can step in right before you're about to decide and screw everything up. Now, it's important to note that both of these ideas were based on a certain model of both the network and failure. So this was based on the asynchronous model of the network. And like I said, there's this idea here that you might drop network packets, you might have errors, a server might start doing garbage collection and pause, but you can't tell the difference between delay and failure. So this is the idea of an unbounded amount of time, right? So it might be, you can't decide that a server has died because it might be possible that it was just delayed for a little bit more than that amount of time. So what does this mean? What do these results mean? And what do they mean for distributed systems? Does it mean that we have to give up hope, that I should forego any of the rest of my PhD and rip up my thesis and throw it away because we're never going to be able to do anything because it's impossible to decide stuff on the internet? Well, here's an analogy that I really like. Have you guys played Candy Crush? A little bit? OK. I haven't played it, though. I played other tiling games. And this is a category of games called Match 3 games. And it's been shown that this category of games is NP-hard. So what does that mean? That means that there exists no polynomial time algorithm to solve all instances of this game. Now, NP, and there's this famous question of P equals NP, and we rely on the fact that certain things are NP hard, like basically all of our cryptography, in order to function in the world. Now, does this mean that we can't play Candy Crush Saga? No. Right? Like, it doesn't matter that it might take you more than the number of atoms in the universe to figure out the answer to a very large game of Candy Crush Saga. I can still play Candy Crush Saga on my phone, and I can still, like, occasionally beat the game. And I bet there's someone out there who always beats the game and, you know, is really good at this. And so I really like this analogy because it means that it helps you understand what this theorem is really saying. And what it's saying is that it's impossible to 100% of the time decide everything on the internet if we can't rely on synchronous messaging. We can 100% of the time decide everything if partitions heal, if we know the upper bound on message delays. Our system might be really slow. It might not be the most ideal system we build, but if we remove this one part of the model, then we can. And also, just because you can't get to 100% all the time doesn't mean you can't function at 99.99% a lot of the time. This is an impossibility result. This means it's impossible to do something all the time. We can still play Candy Crush. We can still occasionally beat the game. And so that's why in my research, I haven't really focused so much on the CAP theorem. Instead, what I really care about is consistency versus performance. So in the day-to-day operating of your system, how expensive is it to maintain good semantics? This is a question that I really care about answering. And what I want to know is how we can reduce these costs while still producing a correct ordering of reads and writes. And can we do this while still handling failures and eventually making progress in the case of failures? So there's been a lot of research about improving the performance of these stronger forms of consistency, like serializability. So here are 4 different types of research, 4 techniques that I found really interesting. So one of them is to basically get around the fact that you don't know what time it is by trying to force everybody to be very, very close in time. So Spanner, a system by Google, is a giant distributed database, and they put atomic clocks in all of their data centers so that they're able to bound the skew. They're able to determine exactly how far it's possible for two clocks to be off. And then they rely on this fact so that they don't have to do as much coordination and communication in order to do some of their transactions. Unfortunately, Spanner is still really slow. So there's been a lot of other techniques developed that are pretty cool. There's this theory of transaction chopping. And the idea here is that if you know you're only going to be doing a certain set of transactions, if your application is doing something and you know what it's going to be doing, it's always going to be issuing the same kinds of queries, you can analyze that set of queries, and you can figure out if you can divide those set of queries up so that serializability is less expensive. And here are two pieces of research from NYU where they've leveraged this technique to get better performance in a geo-replicated system. So they're able to do transactions across a geo-replicated system. Then there's this idea of commutative locking. So I'm pretty excited about commutativity, and this is something that I use very heavily in my own research. And this has been used in different forms. There's this idea of commutative locking in escrow transactions. This is from the database community. It's a very old idea. Abstract data types. And Doppel is a system that I wrote that takes advantage of commutativity to do things per core without communication. And then finally, there are some systems that use deterministic ordering. Basically, if you have a distributed database and you know that people have to commit transactions in a certain order and they all need to commit them in the same order, you can just decide on that order ahead of time. And this can help you get better performance in some cases. Now, our goal here, my goal at least, is to get parallel performance when we're executing transactions on a multi-core or a distributed database. And I think that these are some of the ideas that we're going to use in the future to be able to do that. I think that it's important to think about different concurrency control schemes for popular and contended data. So something that's important to note here is that if your transactions are all on different data, they're not going to contend, and serializability is not actually going to be that expensive. So it's really going to be a problem when your transactions are accessing the same hot, popular data. And if that's really the case, are there special things that we can do for this data to make our transactions go faster? I think commutative locking and abstract data types are really important. And I think interfaces that reveal data types to the programmer are much better than read-write interfaces. So here's an example. So whenever we talk about transaction execution, we talk about reads and writes, gets and puts. And that's what all of the serializability models deal with. However, oftentimes when we are doing things to our data, we're actually following a data type specification. It's a counter and we're incrementing it or decrementing it, or we're taking the max of something, or it's an index and we're inserting into it with some sort of order. And if we know the semantics of the type of objects that we are manipulating, then we can, like some of them are actually commutative, so we can take advantage of some of the techniques I just told you about to get faster transactions. And we can also do all sorts of other different kinds of things with them. And so that's some of what I've been exploring in my research, is how we can use these ideas to get faster transactions. So I'm going to leave you I'm going to give you this quote. This was in the Spanner paper. So I think it's really interesting that Google kind of was one of the first systems in the NoSQL movement with Bigtable. They got rid of all of the relational and query parts of a database. And then they came full circle and they built Spanner, which is an F1, which is basically a giant distributed relational database. And here's a quote from Spanner. "We believe it is better to have application programmers deal with performance problems due to overuse of transactions as bottlenecks arise, rather than always coding around the lack of transactions." And so that's what I want to leave you guys with. Those are the takeaways here. Use databases that are well tested. Don't try to use the latest hotness on the most important part of your system and your product. Use serializable until it becomes a performance problem. So don't optimize too early. And when you get to a point where you have to make a decision, where you have to think about giving up some of your good semantics for performance, think about exactly what it is that you're giving up and what's changing when you move to a system with different models. All right, so that's pretty much it. Thank you very much, and I'm happy to take questions.